Welcome to our comprehensive guide on Azure User-Defined Routes. I'm excited to walk you through one of Azure's most powerful networking features. Think of UDR as your traffic director in the cloud. Just like a traffic controller at a busy intersection, UDR gives you complete control over where your network traffic goes within Azure. By default, Azure handles all the routing for you automatically, and it does a pretty good job. But there are times when you need to take control, whether it's for security, compliance, or specific architectural requirements. Today we'll explore real-world scenarios where UDR becomes essential, and I'll show you exactly how to implement these solutions with step-by-step commands. Understanding UDR components. Before we dive into implementation, let's understand the key components that make UDR work. Think of these as the building blocks of your routing strategy. The route table is like a rulebook that contains all your routing decisions. Each route within that table is a specific rule that says, if traffic is going to this destination, send it this way. The next hop is where you want that traffic to go. It could be a firewall, a VPN gateway, or even dropping the traffic entirely. Subnet association is the final piece. It's like assigning that rulebook to specific network segments. Without this association, your routes are just sitting there doing nothing. Understanding these components is crucial because every UDR implementation follows the same pattern. Create the table, define the routes, then associate it with subnets. Basic UDR architecture. Let me show you how UDR fits into the overall Azure networking architecture. This diagram illustrates the decision-making process that happens every time a packet leaves your VM. When a VM sends traffic, it first hits the subnet associated with your route table. The route table then evaluates all available routes and makes a decision based on the most specific match. Notice how we have multiple next hop options. The default internet gateway that Azure provides, a custom network virtual appliance like a firewall, or a VPN gateway for on-premises connectivity. This flexibility is what makes UDR so powerful. You can route different types of traffic through different paths based on your security and compliance requirements. The route decision engine always chooses the most specific route first. This is called longest prefix matching, and it's a fundamental concept we'll see throughout our examples. Firewall interception scenario. Let's start with one of the most common UDR use cases: forcing traffic through a firewall for inspection. This scenario comes up all the time in enterprise environments. Imagine you have a web tier that needs to communicate with a database tier, but security policy requires that all traffic be inspected and logged. This is where UDR shines. In this setup, we're forcing all traffic from the web tier to go through an Azure firewall before reaching the database. The firewall can inspect the traffic, apply security policies, and log all communications. Notice how the traffic flow changes from the default direct path to a controlled path through our security appliance. This pattern is essential for compliance in many industries. The application gateway handles incoming internet traffic, but all east-west traffic between our application tiers goes through the firewall for inspection. Implementation command flow. Now, let's talk about the practical implementation. Every UDR deployment follows the same logical sequence, and understanding this flow is crucial for success. We always start by creating the route table container. Think of this as setting up an empty rulebook. Then we add individual routes, which are the actual rules that determine traffic flow. The critical step is associating the route table with a subnet. Until this happens, your routes are defined but not active. This is a common source of confusion for newcomers. Finally, we verify our configuration and test connectivity. This verification step is essential because routing mistakes can cause connectivity issues that are difficult to troubleshoot. Throughout this process, we'll use specific Azure CLI commands that I'll show you in detail. Each command has important parameters that control the behavior of your routes. Creating the route table. Let's start with our first command, creating the route table. This is the foundation of everything we'll build. The route table name should follow your organization's naming conventions. I like to use prefixes like RT to clearly identify route tables in resource listings. Notice we're specifying the resource group and location. The route table must be in the same region as the virtual networks you'll associate it with. The tags parameter is optional but highly recommended. In enterprise environments, proper tagging is essential for cost management and governance. This command creates an empty route table. No routes are defined yet. Think of it as creating an empty container that we'll fill with routing rules in the next steps. Creating routes for database traffic. Now we'll create our first route, directing database traffic through the firewall. This is where we define the actual routing behavior. The address prefix 10.0.2.0/24 specifies our database subnet. Any traffic destined for this network will match this route. The next hop type, virtual appliance, tells Azure to send traffic to a specific IP address rather than using default routing. The next hop IP address, 10.0.3.4 feet, is our Azure Firewall's private IP. Make sure this IP is reachable and that the firewall is configured to forward traffic. This single route transforms how traffic flows in your network. Instead of direct communication between web and database tiers, everything now goes through your security appliance. Adding internet traffic route. Next, we'll add a route for internet traffic. The address prefix 0.0.0.0/0 is the default route. It matches any destination that doesn't have a more specific route. By routing internet traffic through the firewall, we ensure that all outbound connections are subject to the same security policies and logging as internal traffic. This is particularly important for compliance scenarios where you need to inspect and log all network communications, both internal and external. Remember, the firewall needs to be properly configured to handle both north-south, internet, and east-west, internal, traffic flows. The same next hop IP address is used, but the firewall will handle these different traffic types according to your security policies. Associating route table with subnet. Here's the critical step that activates our routing configuration. Until we associate the route table with a subnet, our routes are just definitions sitting idle. We're updating the web subnet to use our newly created route table. This immediately changes how traffic from VMs in this subnet is routed. The subnet update command is straightforward, but be careful. This change takes effect immediately and can impact running workloads. Always test route table associations in non-production environments first. A misconfigured route can cause connectivity issues that are difficult to troubleshoot. Once this command completes, all VMs in the web subnet will use our custom routes instead of Azure's default routing behavior. Hub and spoke architecture. Now let's explore a more complex scenario: hub and spoke networking with centralized security. This is a very popular architecture pattern in enterprise Azure deployments. In this setup, all spoke networks communicate through a central hub that contains a network virtual appliance. This provides centralized security, monitoring, and policy enforcement. Each spoke has its own route table that directs traffic to other spokes through the hub NVA. This ensures all inter-spoke communication is inspected and logged. Notice how the hub also provides connectivity to on-premises networks and the internet. This centralized design simplifies security management and provides better visibility into network traffic. The NVA in the hub can be any security appliance, Azure Firewall, a third-party firewall, or even a custom solution. The key is that it acts as the central inspection point. Traffic flow in hub and spoke. Let me walk you through exactly what happens when a VM in Spoke 1 wants to communicate with a VM in Spoke 2. Understanding this flow is crucial for troubleshooting. The traffic starts at the source VM and immediately hits the route table associated with Spoke 1's subnet. The route table has a specific route for Spoke 2's network that points to the hub NVA. The NVA receives the traffic, performs security inspection according to your policies, and then forwards it to the destination in Spoke 2. Return traffic follows the same path in reverse, ensuring that both directions of communication are inspected. This architecture provides complete visibility and control over all network communications while maintaining the flexibility of the spoke networks. Creating spoke route tables. Let's implement the hub and spoke architecture. We start by creating route tables for each spoke, beginning with Spoke 1. Notice the Disable BGP route propagation parameter set to false. This allows BGP routes from VPN or ExpressRoute connections to be automatically learned. In hub and spoke architectures, You often want to allow BGP route propagation so that on-premises routes are automatically available to the spokes. Each spoke will have its own route table with routes pointing to the other spokes through the hub NBA. This creates the centralized traffic flow we're looking for. The naming convention, RT spoke 1 foot, makes it clear which route table belongs to which spoke, which is helpful for management and troubleshooting. Defining inter-spoke routes. Now we'll create the routes that enable spoke-to-spoke communication through the hub. This is where the hub and spoke topology really takes shape. Each route specifies a destination spoke network and points to the same NBA IP address. This creates the centralized inspection point we want. The route to spoke 2 uses address prefix 10.2.0.0/16 to match all traffic destined for that entire spoke network. Similarly, the route to spoke 3 ensures that communication between spoke 1 and spoke 3 also goes through the hub for inspection. The Internet route forces all outbound traffic through the hub as well, providing comprehensive security coverage for the entire spoke network. Forced tunneling for compliance. Let's examine another critical use case, forced tunneling. This scenario is common in highly regulated industries where all Internet traffic must go through on-premises security controls. In forced tunneling, we override Azure's default Internet routing and force all traffic to go through your on-premises network first. The on-premises corporate firewall inspects and logs all traffic before allowing it to reach the Internet. This ensures compliance with data governance policies. Notice how the default route points to the VPN gateway instead of Azure's Internet gateway. This is the key to implementing forced tunneling. This setup requires careful planning because it can impact Azure services that need direct Internet connectivity. Some Azure services may need special routing considerations. Implementing forced tunneling. Let's implement forced tunneling step by step. The key difference here is that we disable BGP route propagation to prevent conflicts with our custom default route. When BGP route propagation is enabled, routes learned from on-premises might conflict with our forced tunneling configuration. Disabling it gives our custom routes priority. This is a critical decision that affects how your network behaves. Make sure you understand the implications before implementing forced tunneling in production. The route table we're creating will override Azure's default behavior and force all Internet-bound traffic through your on-premises network. Always test forced tunneling thoroughly in a non-production environment first, as it can have significant impacts on application connectivity. Creating the forced tunnel route. Here is where we create the actual forced tunneling route. The address prefix 0.0.0.0/0 matches all Internet destinations. The next hop type, Virtual Network Gateway, tells Azure to route this traffic through your VPN or ExpressRoute gateway instead of the Internet gateway. Notice that we do not specify a next hop IP address. Azure automatically determines the correct gateway IP address based on your VPN or ExpressRoute configuration. This single route completely changes how your Azure VMs access the Internet. Instead of direct connectivity, all traffic goes through your on-premises network first. Make sure your on-premises network can handle the additional traffic load and that your VPN or ExpressRoute connection has sufficient bandwidth. Load Balancer integration. Working with Azure Load Balancer introduces special considerations for UDR. The health probe mechanism requires careful attention to ensure proper functionality. Azure Load Balancer uses health probes from the IP address 168.63.129.16 to check if your backend VMs are healthy. If these probes can't reach your VMs, they'll be marked as unhealthy. When you implement UDR, you might accidentally route these health probes through an NBA, which can cause probe failures and remove healthy VMs from the load balancer pool. The solution is to create a specific route for the health probe IP that bypasses any custom routing and goes directly to your VMs. This diagram shows how we maintain both custom routing for application traffic and direct routing for health probes to ensure the load balancer continues to function properly. Configuring health probe routes. Let's implement the load balancer integration correctly. We start by creating a route table specifically for load balancer backend VMs. The health probe route is crucial. It ensures that Azure's health probes can reach your VMs directly without going through any network virtual appliances. The address prefix 168.63.129.16/32 is Azure's health probe service IP. The 32 means it's a host route for that specific IP address. The next hop type, Internet, ensures these probes take the direct path to your VMs, bypassing any custom routing you've configured for application traffic. This is a perfect example of using route specificity to your advantage. The 32 route is more specific than any default route and will take precedence. Understanding next hop types. Let's demystify the different next hop types available in Azure UDR. Understanding these options is crucial for implementing the correct routing strategy. Virtual Network Gateway routes traffic through your VPN or ExpressRoute gateway. This option is perfect for sending traffic to on-premises networks or for implementing force tunneling. Virtual appliance routes traffic to a specific IP address, typically an NVA like a firewall or router. This gives you the most control over traffic inspection and processing. Internet routes traffic through Azure's default Internet Gateway. This is useful when you want to explicitly bypass custom routing for certain destinations. VNET local routes traffic within the same virtual network using Azure's default routing. This is useful for creating exceptions to broader routing policies. None drops the traffic entirely, creating a black hole route. This is useful for security scenarios where you want to block access to specific destination. Route priority and evaluation. Understanding how Azure evaluates routes is essential for designing effective UDR implementations. Let me walk you through the priority system. Azure evaluates routes in a specific order. User-defined routes have the highest priority, followed by BGP routes from on-premises connections, then system routes as the fallback. Within each category, the most specific route wins. This is called longest prefix matching. A /32 route will always beat a /24 route for the same destination. This priority system allows you to create very granular routing policies. You can have a general default route but override it for specific subnets or even individual hosts. Understanding this evaluation order helps you troubleshoot routing issues and design more effective routing architectures. When designing your routes, always think about specificity and how Azure will evaluate multiple potential matches for the same destination. Verification and troubleshooting. Once you've implemented your UDR configuration, verification is crucial. These commands help confirm your routes are working as expected. The show command displays your overall route table configuration, while the list command shows all individual routes within that table. The most powerful troubleshooting tool is show effective route table. This command shows you exactly which routes are being used by a specific network interface. Effective routes include all route sources, your custom UDRs, BGP routes, and system routes. This provides a complete picture of how traffic is being routed. When troubleshooting connectivity issues, always start with effective routes to understand what the network interface is actually seeing. Network Watcher's Next Hop feature is also invaluable for testing specific traffic flows and verifying that your routing is working as intended. Let's explore some advanced UDR scenarios that you might encounter in complex enterprise environments. Service tags in routes are incredibly powerful. Instead of specifying IP ranges manually, you can use service tags like storage (ISTIS) to automatically include all Azure storage IP addresses in that region. This is particularly useful for routing traffic to specific Azure services through security appliances while keeping the configuration dynamic as Microsoft adds new IP ranges. Route table sharing across multiple subnets is another advanced pattern. When you have consistent routing requirements across multiple network segments, sharing a single route table reduces management overhead. However, be careful with shared route tables. Changes affect all associated subnets simultaneously, which can have wide-reaching impacts. These advanced patterns require careful planning and testing, but they can significantly simplify complex network architectures when used correctly. Let's wrap up with the key best practices that will ensure your UDR implementations are successful and maintainable. Always test UDR changes in non-production environments first. Routing mistakes can cause widespread connectivity issues that are difficult to troubleshoot under pressure. Document your routing architecture thoroughly. Network diagrams showing traffic flows are invaluable for troubleshooting and onboarding new team members. Pay special attention to health probe routes when working with load balancers, and remember that asymmetric routing can cause issues with stateful network appliances. Use specific routes when possible, rather than broad default routes. This gives you better control and makes troubleshooting easier. Finally, monitor your network traffic and use Azure's diagnostic tools regularly to ensure your routing is working as intended. UDR is a powerful tool that enables sophisticated network architectures in Azure. With proper planning and implementation, it provides the control and security you need for enterprise-grade cloud networking.